Okay, so let's continue. So we're talking about the confidentiality, and so this is the prototypical setup. And here, Alice and Bob are able to communicate securely if these encoding and decrypting algorithms are good, and then the keys are chosen well here also. So one example of such a very good cryptography, but is completely impractical, is the one-time pad. And here, the main idea is that we have a message, the plain text, and suppose it has n bits in it. Okay. So then Alice and Bob, what they can do is they can generate the key as an n-bit random pattern. And then the encoding to find the ciphertext. Remember that the ciphertext is the encryption, which uses the key and the plain text. And here it's very simple. We just take the bitwise XOR of these two patterns, and then we get the ciphertext C. And to Eve, C here looks completely random. So it carries no information about M to Eve, because Eve has no idea what K is. And the decryption is very simple. It's exactly the same procedure as decryption is the same procedure as the encryption. We just take the ciphertext and we take it modulo 2 addition with K, which is M modulo 2 with K, which is M modulo 2 addition with 0, which is M. Okay, so it's very, very simple. So, I mean, if we have Alice here, for instance, and then the message should be, say, 1011. So this is the plain text. And then the key here is, let's just pick something, 0101. Then the ciphertext, which Eve sees the ciphertext. So what is that? Well, it's the bits XOR between the bits in these patterns. So 10 becomes 1, 01 becomes 1, 10 becomes 1, 11 becomes 0. Okay. So this is what Eve says. And for Eve, this is random. So Eve is out of luck. However, Bob knows the key. So that's 0101. And just takes the XOR between the ciphertext that Bob just receives and the local copy of the key. And then we get the message as being 1 plus 0 is 1, 1 plus 1 is 0, 1 plus 0 is 1, 0 plus 1 is 1. So then we had the message. Okay. So this actually happens to be a completely secure scheme if for each message we have a new key. Okay. So this bit pattern cannot be reused. We have to select a new bit pattern, new random key for every time we want to send the plain text. And that's why this is not very practical. Because as what was pointed out before, how does Alice and Bob communicate the key? Because that is as difficult as communicating M, same number of bits. Okay. But if you want to be really secure, you could do this, right? Alice and Bob, they can meet in a secret room. They can share a key K, which is large enough for all the messages they want to send to each other. And as long as they keep that key private to themselves, they can communicate in complete confidentiality. Okay, but this is to illustrate then that the main problem, so this is, okay, by the way, this is known as a symmetric encryption scheme because we use the same key here and here. It's also called the private key scheme because these keys are private to the communicating parties. Okay. So the main problem is how to share the key in the first place. The key must be secret and shared by only Alice and Bob, and it has the same length as the message. It becomes very impractical. One-time pad is a symmetric cryptography. Alice and Bob share the same key. Okay. Symmetric cryptography is also called private key cryptography. And the main problem is that we need to have this unique secret key, and it needs to be shared between all the pairs of communicating parties. So what does that mean? Well, it means that if we have a network consisting of n users, so if we have then Alice and Bob, well, they need one key to communicate. So here we have Alice and here we have Bob. But if we have also Charlie here, then Bob and Charlie needs a key, Alice and Charlie needs a key, right? And if we keep on doing this, we see that for each user that we add to this, we need a bunch of new keys. And in general, we need n times n minus 1 divided by 2 keys. One per each pair of potential users. So you see the problem if this is the internet, right? A bunch of keys. Okay, so how to solve this? Okay, by the way, before we go on to look at solutions to this, one example of a practical scheme that's used for this is called AES, Advanced Encryption Standard. So if you're interested, you can Google that and read on Wikipedia what it is. Okay, so then we go to the other paradigm. We had this symmetric cryptography, and now we go to asymmetric cryptography. So here, each user has 2 keys, one which is a secret or a private key, and one which is a public key. So we have a secret key, SK, and a public key, PK. And here, the trick is that we use encryption with the public key and decryption with the secret key. Okay? So it's not symmetric that we do the encryption and decryption with the same key. There are 2 different keys. Okay? They're tied to each other, but they're different. Okay. So this means that anyone, Alice and whoever, who wants to communicate with Bob, use Bob's public key. Okay, and Bob's public key is not a secret. It's open. You can post that on the internet, on your business card or whatever, right? It's not supposed to be a secret. So anybody, including Alice, can encrypt the plain text. But what's interesting here is that only Bob can decrypt this, because decryption is done with Bob's private key, and Bob's private key is a secret. Okay. So if I'm Bob, I have a private key and a secret key. The private key is a secret. I keep that to myself. The public key I just give to you. So if you want to talk to me, you encrypt your plain text and send that to me. So the thing is that if you use the encrypt this message cannot be read by any of you because you don't have my private key. Only I can read it. So this is the beauty of the scheme, right? So only Bob can decrypt, anybody can encrypt. So what do we have here in our prototypical setup here? We have Alice and we have Bob. So Alice has a plaintext M. There is an encryption algorithm that uses a key. That key is Bob's public key because this message goes to Bob. So PK is using here. There's a ciphertext here, which is some encryption of the private key and, public key. Okay, P stands, could be also private, but it's not here. It's public key and the plain text. E cannot decode this if the scheme is secure. However, Bob, knowing its his secret key, can decrypt this. So, questions?
I don't understand how you can encrypt it. If you know the encryption code, don't you know the decryption inverse?
No, so we should not think of this as the one-time pad where you use the decryption and encryption using the same key. So this is using a completely different methodology, which is super interesting, but way out of scope for what we have time right now. So just believe me, it is possible to do encoding with one key and decoding with another key. Okay, because these are tied to each other in a very special way, but that way is, given the public key, there is no way we can figure out the secret key. Okay, but they're generated in a special way, so they are tied together. Right?
Even if you have 10 years and all computing?
If you have 10 years and all the computing power, you can do this, right? Yeah. So NSA can read your emails. Right? So yeah. No, so it sounds strange, but it can be done, right? So what the cool thing about this, and this is a fairly new invention. So this was maybe in the 70s that they started to think about this, right? So before that, it's all private key cryptography. And okay, 70s might sound like a long time ago, but think that encryption, we have done that for thousands of years, right? Okay. So the public key is not a secret, so anybody can encrypt messages, also the people that Bob have never met. So this is nice because we don't have to exchange keys, right? As soon as I can publish my public key on the internet, whoever can access that web page can communicate with me securely. Okay. The secret key, however, is a secret. Okay, so that needs to be kept secret, and that means that only Bob can decrypt the message. Key distribution, therefore, is easier than for the private key encryption, but certainly not unproblematic. We will see later on that this is actually a headache, right? But it's easier at least. So the main drawback with this is that the encryption and decryption of this is 100 to 1,000 times more complicated than the encryption and decryption of a symmetric key crypto. So there is no free lunch. So it costs about 100 to 1,000 times more computing power to do this. So what do? Well, here's the genius, right? We use public key crypto to transmit the key for private key crypto, and then we use the private key crypto for communicating large amounts of data. Okay? So, practical solution. Alice and Bob use public key crypto to share a key. Okay, we call that the session key. Alice and Bob then use their private key crypto, maybe AES or something like that, with the session key that they just now shared, right? And then communicate large volumes of data. So this can be done 1,000 to 100 times more efficient than this per bit, right? So this is the cheaper way to do that. And then when the session is over, when we're done communicating, we throw this key away and Alice and Bob are done. Okay. So we use the power of public key crypto to share the secret key. And once this is done, we use the secret key. Questions? Okay, so here, this means that Alice and Bob have never met before, but they can still use private key crypto. So for instance, maybe Bob is Amazon and Alice is first-time customer. So how are they going to communicate securely? Well, this is the way to do it. Okay. All right. Now we know how to do confidentiality. So that the objective here is to make sure that Eve is unable to decode a single bit of the plain text. Okay. Is that enough? No, it's not. So we also want integrity and authenticity often. Okay. And sometimes we don't want to have confidentiality, we don't need it, and then we just are interested in integrity and authenticity. So what is this? Well, cryptography can be used to provide this. Authenticity, that means that verification that messages come from the correct sender. So, for instance, when you get an email from Google saying that you won €1,000,000, right? Do you trust this? No. And why is that? It's because email does not provide authenticity, right? So we see that this could be useful, right? Integrity means that a message has not been altered in transmission. This could be also very important. Suppose I'm Microsoft, for instance, and I'm patching my operating system. I send out a patch on the internet for people to update their computers. Now a hacker sends out a faulty patch, so half of the Windows machines are then updated with the hacker's operating system, and all those machines are then infected with viruses. So a receiver of an update from Microsoft Update needs to be able to figure out, is this patch original or not? And does it come from Microsoft or from somebody else? Here, the content of the operating OS update is not a secret, right? But it's important that it's correct. So here, secrecy is not important, but integrity is very, very important. Okay, so another example is when interacting with our bank over the internet, how do we know that the web server we're talking to is really the bank server? How do we know this? How do we know that the money transfer goes to the right destination and has the right amount? Okay. Authenticity, integrity. Right. And often these goes hand in hand. We most often want to have both of these, right? But for instance, it's the case when I'm Amazon, for instance, it's, never mind that. Okay. Confidentiality does not prevent tampering with the message in general. Okay. So let's see that. For instance, if we have the one-time pad here, so here we have an eavesdropper who's interested in decoding the message. Now let's change the attacker to Trudy. Trudy for intruder. Okay. So Trudy would like to mess up the message to alter that. Okay. So Trudy, instead of allowing this ciphertext to go through the network, she changes this to C prime by flipping a bit in the ciphertext 0110. Okay. Trudy has no way of figuring out the message, but she can manipulate the message, because what we do here is that when Bob is decoding C prime, it gets 00 and then a 0 here. So Trudy is able to flip a bit in the plaintext without knowing the plaintext by manipulating the ciphertext. Okay, so flipping this bit flips this bit. Not good, right? So confidentiality is not good enough, right, for this. Okay, so what to do? There is something called message authentication codes, or MACs. Okay, so this is not medium access control. It's message authentication codes. So how do they work? Well, they work like this. We have the plain text, and then we have some type of encryption here called the MAC code that is driven by a key K. And it produces a tag T, which is a function of the plain text and the secret key. This secret key is a secret to Trudy. However, it's not a secret to Bob. So Bob knows K. So this is almost like this symmetric cryptography we had before. Now, the message goes in plain text here, because it's not, confidentiality is not needed in this setup here. We will see later on that we can do encryption of this also for sure. But so the message goes through this, and then we have the tag goes through this. And Trudy here can manipulate both M and T and output M prime and T prime to Bob. Okay. Bob has access to a verification algorithm that takes as input the key, the secret key, and whatever message and tag it received. Okay. And then it outputs a decision B here, and B could be 0 or 1. 1 if everything is okay, 0 if it's not okay. So Bob here will accept the message M prime if B happens to be 1, if the verification says it's okay. So that's the main setup here. Now, for a secure Mac here, it is actually impossible for Trudy to forge a message, that is to output an M prime and T prime, which is not equal to what it was sent. So either it's a difference in M or a difference in T or a difference in both, such that B is equal to 1. It's impossible to do. So Trudy cannot forge messages. Okay? I'm not going to tell you how to do this, but it's possible to do this. Okay? And again, the tag here, why this is possible is because the tag depends on a shared key. Okay. So when B is equal to 1, then Bob can be sure that M is actually from Alice, because Alice is the only one that knows the key. So here we also have some type of notion of authenticity. So when Bob noticed that verification puts out an OK here, he knows that M and T, M prime and T prime, came from Alice. Okay, because they are the only people that share the secret key. Okay, so some level of authenticity is provided here. However, Bob cannot prove to anybody else that M came from Alice. Okay, and that's something that sometimes we want to do. Okay, so we'll see a scheme where we can actually do that later on. That Bob can go to somebody else and say, hey, I got this from Alice. It's actually from Alice, and I can prove it. Here, Bob cannot do that because he and Alice are the only one that knows this key. So even if Bob shows the K to prove for somebody else that this message came from Alice, well, Alice could say, I don't have that key. It wasn't me. Right? So there is just a small level of authenticity here, right? Okay. To have greater control of authenticity and also to avoid the problem of key distribution here, we can use a public key mechanism for doing this also. And the only difference is that these are now called signatures rather than message authentication codes. Of course, the technology behind it is completely different, right? But the use of it is the same. So Alice here has some plain text M, and Alice's have a keys here also, a secret key and a public key, okay, just as we had before. Now, Alice can sign the message M by using a signing algorithm, which is driven by Alice's secret key. Okay. And this signature, sigma here, is then a function of Alice's secret key and the plain text. And then we have Trudy in the middle. Trudy can do something with the plain text and with the signature. There is a verification mechanism here. And the verification mechanism here works on the public key of Alice. So it's a function of the public key of Alice, M prime and sigma prime, which Bob got from the network. So public key crypto, analog to the Mac here. Signing is done with the secret key. Verification is done with the public key. Okay. Only Alice can sign, right? Because only Alice has the secret key. But anyone can check the signature because everyone knows the public key. Okay. So this is good because then only Alice can sign, but anybody can check the signature. See here. So first of all, Bob, if this is a secure scheme, Trudy has no way of forging M prime or sigma prime. Okay, so there's no way for her to be able to forge this. But moreover, Bob can convince other persons that M and sigma is from Alice. And moreover, Alice can never deny that she has signed this message. Why is that? Because we have, this is publicly known information that this is the public key of Alice, and it can only belong to the secret key that Alice has. So the only way Alice can say, I didn't sign this, is that Alice says, okay, somebody stole my secret key. But that defense is like the dog ate my homework, and it's kind of weak, right? So authenticity is implied here, but only, of course, if the public key really belongs to Alice. So we will tackle that problem shortly here. So questions? Yes?
So in this case, anyone can read the message?
Yes, exactly. So here, we can think of this as being Microsoft, for instance, and they're sending out a patch to their operating system. It's not a secret per se, but really the Bob here who wants to update his computer really wants that the patch here that he receives from the network comes from Microsoft and not from a hacker. Right. Okay, a small detour here. The problem with this is the same as before, that the computational complexity here is about 100 to 1,000 times more than for Macs. Okay, so what we can do instead is to, instead of signing here, okay, so the computational complexity depends on the size of this message. Okay, so suppose this is a Microsoft update. It could be hundreds of megabytes, right? So that could be quite complex, both to sign it and also to verify it. Okay, signing is probably not a problem because Microsoft has computers, right? But your old, poor Windows machine here, you want to save that somehow. So what to do then? Well, enter a really cool thing called hash functions. So a hash function is something that can compute a summary of a large block of data. And that summary is unique for that large block of data in the following sense. So suppose we have an n, it can compute a bit pattern, n bit patterns x of a message m of an arbitrary length using this. The hash function here operates on m, and these could be megabytes, gigabytes, whatever, and this could be like 256 bits or so, or 512 bits. So, okay, so there is this type of function, okay? And the digest x is similar to what you would say, for instance, in a CRC or something like that. So it somehow summarizes this large block of data in fewer bits. But the difference is that it's impossible, i.e. very hard, okay, to find two messages with the same hash. Okay, so a good hash function, then there's no known pair m and m prime that produces the same hash. Okay. So how can we use that? Well, if there's nobody ever found two messages here that produces the same hash, then the hash itself is a unique identifier for the message. Okay? So we can use the digest instead of the message for authenticity and integrity. So if no pairs m and m prime are known to have the same digest, then the hash function is said to be collision free. And there actually exist such functions. So for all practical purposes, we can view the digest x, which is the hash function operating on the message, as uniquely defining m. Okay. So we can sign x rather than m in order to prove integrity. And this will save computational complexity because x is much shorter than m. So m could be this Microsoft OS update, like hundreds of megabytes, and x here could be 256 bits. So to sign, to go through this signature procedure and verification procedure on x is much easier than on m. So practical hash functions is MD5. Maybe you've seen this sometimes. It should no longer be used because it has one has found problems with it, collisions and so forth. There's something called SHA-1. It's not safe either. SHA-2, which people seem to think is okay, even though it has some weaknesses, and SHA-3, which is the next generation of this, right? So here we see again, right? In the beginning, one did MD5 and thought, this is pretty good. And then people were attacking it, and found weaknesses with it. And then they say, okay, you should not use that anymore. You should use SHA-1 instead. And then the same thing happened here. And one should now use SHA-2. So the next time you get a patch or something like that, you can see whether you have an MD5 tag on it. And it's quite often still used, right? So here's I mean, it's unfortunate, but here's something which is used, which has weaknesses in it. I don't think Microsoft is using this, but maybe somebody else. Depends on what the cost is, of course. Okay, so what do we do here is that we have this hash and sign paradigm. So instead of doing as we did before, is that we're signing the message, we are now signing the hash of the message. So we take the message, we feed that through our hash function. So here we have our hundreds of megabytes. Here we have 256 bits. It's a quick operation to sign that. So what we sign is using the secret key of Alice. Okay, so Alice is signing, so she needs to use her secret key. She's the only person that has the secret key. Okay, so she signs this. Trudy is messing this up, but Bob will only accept M prime here if the verification goes through. And what we are verifying now is using the the public key of Alice, the hash of M prime, which is computed then locally at Bob, and the sigma prime, which is the signature that was delivered to Bob. Okay. So example of these practical schemes, there is something called the RSA FDH or RSA PKCS number 1 version 2.1. I don't know, whoever invented this probably did not get a Christmas bonus, but yeah, that's what it's known as. Okay, questions on this? Okay, so using of hash functions in this is just to save computational complexity. Security is the same, more or less. Okay, now here, Bob here is verifying that the message came from Alice by using Alice's public key. How does Bob know that this bit string is Alice's public key? This is a problem, right? How does he know this? So doing that, one can use, so this is the way to do that. One introduces a third party that keeps track of people's public keys. Okay, it's called the certificate authority. So checking a signature for authenticity uses the sender's public key. But how does Bob know that some bit pattern, let's call it PKA, is the public key of Alice? Bob has never met Alice before. Okay. However, Bob knows a person called Charlie that has certified that PKA is Alice's key, and Bob trusts Charlie, and then Bob can trust that PKA is actually Alice's key. Okay. So Charlie here is a certificate authority. Okay, and that is some type of trusted organization. It could be like a governmental agency, or could be, now I lost the names of these. You probably recognize the names when you see them. VeriSign. I forgot. But anyways, they're trusted organizations with well-known public keys. Charlie has a public key which is well-known, and a really, really secret private key. Secret key. So Charlie can provide Alice with a certificate. So what is a certificate? Well, a certificate is produced by Charlie, and it certifies something about Alice. And it's a signature signed with the private key of the CA, saying that the public key pka belongs to Alice. Okay, so this is a certificate. So if we trust Charlie and we know the public key of Charlie, we can verify that this signature is true. This is actually something that Charlie said. Okay. And then if we trust Charlie and Charlie says that this key belongs to Alice, then we can safely trust that Alice actually has this key. That's the public key of Alice. So what do we do? Alice sends the certificate to Bob. Bob can verify that it's been signed by Charlie because Bob knows the public key of Charlie and thereby trust that pka is actually Alice's public key. Questions? Okay, so as long as we have this Charlie, the certificate authority, everything is okay, right?
Seems a bit sketchy.
Yeah. So, wait a minute. How does Charlie know that Alice has had this public key? Okay. Alice actually has to visit Charlie with her key and prove her identity. That's how it's solved. So, VeriSign, for instance, if Amazon would like to have a certificate, Amazon has to go to VeriSign and say, we're Amazon, here's our public key. Can you certify this? And they say, okay, you can do that if you show me some ID and things like that. So, I mean, it's a complicated process of doing this, right? But it can be done. Okay. How does Bob know Charlie's public key? How do I know the certificate authority's key? It's hard-coded into the operating system or into the web browser. So, when I buy this, it's hard-coded into the operating system a number of public keys to certificate authorities. And when I update my Google Chrome or whatever, it's there. Is this perfect? No. Is this a problem? Yes. Do we have anything better? No. Okay. Because the problem is that there are many certificate authorities. How can we trust all of those? We really can't, right? So sometimes it happens rarely, but it happens that certificate authorities get compromised. Okay, and then that is a problem, surely. So what do we do then to handle errors and things like that? Well, in practice, these certificates expires after some time. Okay, so they have a best before date, and after that they should not be used. So, and that could happen, for instance, when the secret key is somewhat compromised, or when, for instance, we hand out public keys to all the employees in a company, get specific public and secret keys, and when that person leaves the company, we should revoke that certificate, which sometimes gives access to internal systems and so forth. Right? So there is a time on all these certificates. And also there is a revocation list. So if something bad happens, then one can put that certificate on a blacklist, and those should not be used. Certificates are encoded in this format called X509, which is much more complicated than what we illustrated here. But the gist of it is in this. So you had a question?
Yeah, how do you update the certificates in your computer?
So typically, okay, I am as a user, I don't have a certificate, right?
No, but your database.
Exactly. So when I'm accessing a website, I get the certificate from that from the website, and then I investigate that whether I believe it or not by contacting a certificate authority to check whether this is correct or not.
You said something was hard-coded in the computer.
Yeah, so these are the public keys to where is it? to the certificate authorities. So the only way to get an update on that is basically to get a patch for the operating system or for your web server, or web browser. Right. Yes. Okay. TLS, to finish off. So there is something called transport layer security. So this is sort of like a layer which is in between the application layer and the transport layer, typically over TCP, which allows application protocols to talk over TCP in a secure way. Okay. So TLS is a more modern version of the earlier SSL that you might have heard of, which stands for Secure Socket Layer. So TLS can be used by application protocols to provide confidentiality, integrity, and sometimes also authenticity. I'm getting out of steam here. So this is optional, but it can be used. So TLS is used by HTTPS, the secure HTTP. Right? So when you log on to Gmail or something like that, you are using not HTTP but HTTPS, which is HTTP over TLS. So TLS makes sure that whatever you communicate with the web servers is encrypted, and also that you are actually talking to the right web server. So this is very good for Gmail, for instance, where you have a web interface, you write you read your emails. You don't want anybody else to read your emails. And you also want to be sure that you are talking to the Gmail server and not to a hacker server. Right. So one should, of course, use this. So if you're interested also, if you next time you log on to a site which has this HTTPS protocol, you see typically on to the left of the address field, you see like a small symbol saying that this connection is secure. If you click on it, you can see the certificate and the certificate authorities and the type of encryption which is used and so forth. It's kind of interesting. Okay. So at the end of the day, security is only as good as the people that use it. So basically, we have a lot of secure protocols and secure mechanisms and so forth. What causes the most problems, I would say, is still the humans. Okay. So no security technology is secure if it's misused or used in the wrong way. So for instance, when you are forming your own startup and you would like to have some security and so forth, spend the money to bring in a security expert to do the work for you. Because so many people have tried to do their own security and they're all failing. Right? Because this is actually much more complicated than one could think. So one can think things are really secure and they turn out to be trivial to break. Okay. So bring in experts for doing this. So many problems then occur to user mistakes or carelessness or incompetence. Okay. So what is mistakes or carelessness? Well, weak passwords, answering phishing emails. So your email quota has expired. Could you please log on to this site and give me your credentials for the web server? I actually had a PhD student that did that once. So, and I don't know what he was thinking. Not at all, I guess. Obviously, we don't do that, right? But my mother could do this. I mean, she got called up by Microsoft with an English accent. Said, okay, could you please install this on your PC? Luckily, she didn't have a PC, so yeah. I got called up 2 weeks ago. Right. So, this is unfortunate. So, and then many problems become from badly configured systems, unpatched operating systems, bugs in implementations. This actually happens. I mean, if you heard of the Heartbleed bug, somebody heard of this? This was a bug in an OS routine that's been there for a long time. And then unapproved use of secure algorithms. So one takes all these components and one put them into an order which is not secure. And it's not obvious for the non-expert how to do this. Okay, so that finishes off everything I had to say about security. And if you go on Ping Pong, there are two links to online lectures on security that gives a little bit of added information, I guess. But what I said today is basically what you need in order for passing the exam. So you don't have to read much more than this, if you understand this, of course. And that could be problematic. And if you don't understand this, you should consult your favorite book or the internet to figure out what's going on. Okay, so I'll see you on Friday. That's the last lecture. So Friday is going to be review, talk a little bit about the rules when it comes to the exam. And whatever questions you have, I'll be happy to try to answer them. So see you on Friday.